Okay, so this is a quick video on induced voltage, following on from the force on a charge stuff in the previous one. Just a quick review of that. If you've got a charge moving through a magnetic field, two things we need to be concerned with: the direction of the force, which we can find using the right-hand rule, where your fingers point in the direction of the magnetic field, your thumb is the direction the particle is moving, and the direction your palm faces is the force on a positive charge, and the back of your hand is the direction of the force on a negative charge. And we can find the size of the charge using the formula F equals BQV. So we're going to be using those as we go through this presentation. So if we think about, if we've got a moving conductor, so in this case we're going to be talking about a piece of wire or a piece of metal moving through a magnetic field, moving in this case this way. So we've got the conductor has to move so that it's cutting across the magnetic field. Okay, so crossing across the magnetic field lines. We'll come back to that a little bit later. Now, the conductor is made up of positive and negative charges, protons and electrons, essentially. There's neutrons as well, but they have no charge, so they experience no force. Now, if we think about the positive charges and apply the right-hand rule with the fingers pointing into the screen, the direction that the magnetic field's going, thumb pointing to the right, the direction that the rod is moving. The palm is facing up, so the positive charges will experience an upwards force. Okay. However, the positive charges are protons, which are in the nucleus, and they're fixed in place. Inside a solid, the nucleus can't move. So the positive charges don't actually move anywhere. However, the negative charges, if we do the same right-hand rule, they've got the opposite charge. They will be in the force in the opposite direction. They experience a downward force. And some of the electrons, some of the outer electrons, are free to move, particularly in like a metal. So as the conductor moves, the mobile electrons are forced downwards. So we get a motion of electrons towards one end of the conductor. Okay, so in this case, the bottom, due to the orientation of the magnetic field in the direction that it's moving. So we end up with one end of the conductor, the top in this case, has more protons than electrons. There are still electrons there. I haven't drawn all of them. It's just some of the free electrons have moved down. But overall, it will end up with a positive charge. We'll have more protons than electrons. And the other end has more electrons than protons, so we'll end up with a negative charge. Now, that what we call that is a separation of charge. Okay. Now we had to do work to move those electrons down. A force had to be applied, and they moved a distance. So work has been done. So we've increased the potential energy. In this case, it's electric potential energy of the charge. And when you give charges energy, that's what a voltage is. So by increasing the electric potential energy of the charge, we've induced a voltage. Okay, but it's worth pointing out that this only happens while the conductor is moving. Like in the situation here where that rod has stopped moving, those electrons would not all still be at the bottom. They would have redistributed back throughout the entire rod. So it's only while the rod is moving that you get that voltage induced. Okay, so that's why we get a voltage, because that separation of charge increases the potential energy of those charges. So there's two things we need to know about that voltage. First of all, which way round is it, like the orientation of the voltage, and secondly, how big is that voltage? We'll start with the orientation. So essentially, if we've got a rod and it's moving this way, I'm going to say upwards in this case, I want to know which end of the conductor, M or N, will be positive and which will be negative. Okay. Now, I'm going to consider a positive charge inside that wire. Okay, there's lots of charges in there, but I'm just going to consider one positive charge. And we can consider the direction of the force on it by using the right-hand rule. Okay, now just to be clear, what's actually happening inside the wire is that the free electrons can move, okay, and that the positive protons stay fixed in place. But what we're doing here, what I'm doing is we're imagining what would happen to a free positive charge. Like if there was a free positive charge that could move inside the wire, what would happen to it? Because that's what conventional current is. Current is the movement of positive charge. So that's why I'm imagining what's going to happen to a positive charge here, okay? So let's take for now just that charge. Let's not worry about the wire for a second. Think about this charge inside the wire, okay? And we're going to think about what's going to happen to it. So if we apply the right-hand rule in here, fingers pointing into the screen, thumb is pointing up, and it's a positive charge, so my palm is facing towards the left, towards M, so that means there is a force exerted on that charge towards M. So if we think about that inside the conductor, a positive charge would move towards M, okay? We could also consider what would happen to a negative charge. The negative charge, because it's got the opposite charge, will move in the opposite direction. So a negative charge would be pushed towards N, to the right. So that will end up where we would have M would be positive and N would be negative. So we can use the right-hand rule to figure out the orientation of the voltage. So which end would be positive and which end would be negative. The next thing we need to consider is the magnitude of the voltage. So how many volts are we actually going to get? So if we take our conductor, now at this point we're considering it's got a length L, moving at a speed V. Again, it's cutting across the magnetic field. And I'm going to consider a positive charge, Q, inside that conductor. Now, if the rod's moving that direction, it will experience a force towards the left, okay? Now, if we imagine that charge moving through the rod, okay? It's moved from one end to the other, so it's moved a distance under the influence of a force. If you move a distance under the influence of a force, you have done work, okay? And we can evaluate how much work was done to move the charge by calculating force times distance, okay? Now, in this case, the force that's been exerted is a magnetic force, which we can evaluate by using BQV. So that's the magnetic field strength multiplied by the charge multiplied by the speed that the conductor is moving. And the distance it moves is the length L. So we can write that the work is BQV times L, or just BQVL. If we then want to calculate the voltage, if we just remember that voltage is defined as the energy per charge, or in this case, because energy and work are the same thing, we can calculate it as the work done divided by the charge. And we have an expression for the work that we just figured out. So we can express voltage as BQVL divided by Q. The Q's cancel out. So we're left with this expression. The voltage is B, the magnetic field strength, multiplied by the velocity that the conductor is moving, multiplied by the length of the conductor that is inside the magnetic field. Any length outside the magnetic field doesn't matter. And that gives us our induced voltage in volts. Now, that formula only applies when the magnetic field, the velocity, and the length are all perpendicular to each other. Okay. The conductor has to be cutting across the magnetic field in order to actually induce a voltage. So, for example, in this case where the conductor is moving up the screen, that would be cutting across the field. The way I always kind of imagine this is, if you imagine the magnetic field lines as being like blades of grass, you have to cut the grass, okay? You have to be cutting across those. You can't comb the grass. So, for example, if that wire, that conductor was moving to the left, that wouldn't be cutting across the line, so you would induce no voltage. The same to the right. Or if it was moving into the screen or out of the screen, it wouldn't be cutting across those magnetic field lines, so it wouldn't be inducing a voltage. So it has to be cutting across the magnetic field lines. So if it doesn't cut across the field, if it doesn't cut those field lines, the induced voltage is zero. So here's an example of some sort of question. I'm going to use the context of a plane. So this is a plane. We're viewing this from above. This particular plane has a wingspan of 36.8 meters and is traveling at a velocity of 260 meters per second. And it's flying through a magnetic field like this, okay, with a strength of 60 microtesla. So there's 4 questions here. Which part of the world is the plane flying over? Which wingtip, P or Q, is positively charged? Calculate the voltage induced across the wingspan of the plane between P and Q. And explain why that voltage cannot be used to power a low power LED inside the plane. So if you want to have a go at those, I'm going to pause the video now, have a go at them, and then play it again when you want to go through the answers. Okay, assuming that you've done that, or just want to see the answers now. So, starting with question 1, which part of the world is the plane flying over? Now, first of all, the magnetic field is vertical. Okay, that means it has to be over one of the poles. That's the only place in the world where the magnetic field is vertical. So it's either at the North Pole or the South Pole. Secondly, what direction is that magnetic field? Okay, the magnetic field is going towards the ground, because this is viewed from above, remember. And remember that magnetic fields go from north to south magnetic poles. So this is going, the magnetic field is going towards the ground, so towards the Earth, and magnetic fields go towards south poles. That means the plane is above a south magnetic pole. And remember, there's that slight oddity around how the magnetic poles and the geographic poles are opposite. So if it's above a south magnetic pole, that means it's above the Earth's north geographic pole. So it's above the Arctic. Okay, secondly, which wingtip, P or Q, is positively charged? We can do this using the right-hand rule, okay? So if you point your fingers into the screen, the plane's flying towards the right, so your thumb's pointing towards the right, and your palm is the direction of the force on a positive charge. So a positive charge would experience a force towards P, which means a negative charge would experience a force down towards Q. So wingtip P is positive and Q is negative. All right, question 3. Calculate the voltage induced across the wingspan of the plane between P and Q. So we can just use the formula V equals BVL to calculate this and plug in the numbers that we've got. So the magnetic field strength is 60 microtesla. Micro is times 10 to the negative 6. So 60 times 10 to the negative 6 times the velocity, 260, and times the length, 36.8. And that gives us a voltage of 0.57 volts. All right, the fourth question. Explain why that voltage cannot be used to power a low power LED inside the plane. So, as I draw on there, you could just connect wires to either end of those wingtips and connect it to like an LED or a light bulb or something inside the plane. Why would that not work? It isn't anything to do with how much voltage there is. It just fundamentally cannot be used inside the plane. I'm going to draw a little diagram here. Let's imagine down on the side there we've got the magnetic field, and we've got our circuit sort of moving here. Okay, now the right-hand side of that circuit is the wings. Okay, P and Q, the wingtips, and then we've got the left-hand side of the circuit is the rest of the circuit needed to connect it to the light bulb. Okay, now we've already figured out between P and Q we're inducing a voltage of 0.57 volts, and P is positive, so that's kind of like this. If we've got a battery being, or a power supply on that right-hand side providing 0.57 volts. Now, if it was just that, that would power that LED, assuming it had enough. But the thing is, with this circuit, you've also got the side on the sort of return loop, I call it, on the other side between X and Y, which has the same length and is moving the same speed through the same magnetic field. So that means that this side XY will also have the same voltage induced in the same orientation, meaning that the positive will be at the same end. Okay. Now, if you look at how those are connected, that's kind of like connecting two batteries together the wrong way round. So they're opposing each other. Okay. So the reason you can't use it is that the wires connecting the wingtips to the LED have the same length and are moving the same speed through the same magnetic field. So they have the same voltage induced across them, but in the opposing direction. That means the net voltage, the total voltage induced, is 0, which means if there's no voltage, there's no current, and if there's no current, the LED doesn't work. Okay, that's quite a common sort of exam question, things like that, like you induce a thing. So, you're inducing a voltage, but you can't use it. Why not? Because you're inducing the same thing on the other side of the circuit. But the issue is then, how do we actually get current flow? Because this is how most electricity is generated, by moving a conductor through a magnetic field. All electrical generators use this principle. Okay, so how does that actually happen? If we consider again positive charge in there, that's going to experience a force to the left. Okay, now the trick is the return loop, the rest of the circuit has to be outside the magnetic field, like this. Okay, because then that part of the circuit has no opposing voltage induced across it. So we've only got voltage being induced across one part of the circuit. Okay. Remembering that conventional current will flow in the circuit in the direction that a positive charge would move. So if the positive charge there would move to the left in that part of the circuit, you'd get current flowing anti-clockwise around that entire circuit. Okay. A note on this, just an interesting aside. If you do that, you've now got a current flowing through that conductor. And that conductor is inside a magnetic field. One of the first things we talked about with magnetic fields was when you put a wire carrying current in a magnetic field, it experiences a force. Okay. In this case, if you were to use the right-hand rule for the force on a conductor, you find that the force is actually downwards. Okay. The force that is exerted will always oppose the motion. Okay. So if that wire is moving up the screen, as in this case, there would be a force downwards. If it was moving down the screen, there would be a force upwards. Whatever force it generates will always oppose what's going on. That means that the wire would eventually stop, and if you weren't pushing it. Okay. So if you actually want to continually generate electricity, you have to keep pushing it to overcome that opposing force. Okay. So quick summary then. Induced voltage. If we have a conductor moving through a magnetic field, you get a separation of charge, so one end becomes positive, the other end becomes negative. That increases the electrical potential energy of the charges, so induces a voltage along the moving conductor, okay, as long as the conductor is moving across a magnetic field. And it has to be cutting across the magnetic field lines. We can use the right-hand rule for the force on a charge to figure out the orientation, to which end would be positive and negative. And we can use the formula V equals BVL to calculate the magnitude of the voltage. But remember, that formula only applies when those things are all perpendicular, BV and L. The conductor has to be cutting across the magnetic field, and if it is not cutting across the magnetic field, the induced voltage is 0. Cool. Hope that helps.